All right, differential equations, day number 3, the homogeneous method for finding solutions, general or particular, to differential equations. So in some cases, a differential equation is not traditionally separable, like we worked through in lesson number 2. The homogeneous method is one of the many techniques used to resolve this. So the homogeneous expressions for y prime involve a substitution. So it's kind of like a substitution method for finding a solution to the differential equation. Homogeneous method applies when you see the application of the following substitution, either u equals y over x or y equals ux. Now if y equals ux, I could use the product rule on this to find dy dx, which would relate u and y with respect to x. So using the product rule, I would take the derivative of u with respect to x times x. So I would call the derivative of u with respect to x du dx multiplied by x, right, plus the derivative of x times u. So using the product rule, I can have the substitution dy dx is equal to du dx times x plus u. So I'm going to highlight these two items as very, very influential in this process. Now, at times, I might refer to this substitution here, u equals yx, depending on the situation. But those three things are huge when it comes to being able to then separate and integrate. Okay, let's get started with an example. Okay, example A. Find the general solution to the homogeneous differential equation below. Now, when I think of a homogeneous differential equation, it's a differential equation that I can't separate in its current form, right? And I see some form of y over x or x over y, and they're related in that way. So first thing I'm going to do, as I did in the separation of variables lesson, is I'm going to write this as dy dx. Okay, and I'm going to rewrite it as x plus y over x. Okay, now I'm going to use the substitution that we used on the previous page where x equals, y equals ux. Okay, and understanding that dy dx, when I use the product rule on that, is equivalent to du dx times x plus u. Okay, so I'm going to use this substitution right here, y equals ux, and in here for y, I'm going to plug a ux. I'm going to use the substitution that dy dx equals du dx plus u, and I'm going to substitute that in right here. So I would have, with both of those substitutions, du dx times x plus u is equal to x plus ux over x. Okay, now I have, in this process, I have isolated and I have cleared out that variable y. Okay, now I'm going to keep in mind at the very end that u equals y over x, when I find my general solution to this differential equation. Now what I want to do is this will end up being separable in terms of u and x. So check out what I do here. Okay, not a whole lot of change here on the left side. I'm just going to leave this as du dx times x plus u. On the right side, I'm going to simplify. I'm going to reduce out an x, which would make this 1 plus u. Okay, now this ends up being relatively simple, as when I subtract a u from both sides, I end up getting du dx times x is equal to 1. Okay, now this is separable. I've gotten this into a separable form. I'm going to bring everything x to one side, which means that I would have du is equal to 1 over x dx. Okay, I'm now allowed to work a little integration since this is separated. that means that u, the integral of du, will equal the natural log of x plus c. Now, I don't have a initial condition, so I'm just going to work with the general form. And now this is where I take my u equals y over x, and I'm going to do a substitution. So that means y over x is equal to the natural log of x plus some constant, and therefore y is equal to x ln of x plus cx. There is our general solution to this differential equation. All right, so just to reiterate, these items right here are your foundational items in finding the general or particular solution to a homogeneous differential equation. Let's look at another example. All right, as you can see, I've pre-written my friends up here, the substitutions that are necessary in a homogeneous differential equation. So I see y prime equals y squared plus xy over x squared. I'm going to rewrite in the form that I like to work with. Dy dx is equal to y squared plus xy over x squared. Now, if y equals ux, then y squared equals ux squared. Okay, and if dy dx equals du dx times x plus u, I'm going to do that substitution like right now. So I'm going to rewrite the left side as du dx times x plus u. I'm going to rewrite the right side. Y squared is going to be u squared x squared. Right? That's ux squared. Okay, and xy will be equivalent to x times ux, which will be ux squared. This is all going to be over x squared. Okay, let's do a little bit of work here. I can reduce an x squared out. So I'm left with du dx times x plus u is equal to u squared plus u. Okay, you can see that I reduced out the x squared in each of the terms. So I'm left with u squared plus u. All right, so I'm going to subtract u from both sides. That leaves me with du dx times x is equal to u squared. This is separable. So I would have 1 over u squared du is equal to 1 over x dx. Time for some integration. Okay, the antiderivative of 1 over x is natural log of x plus c. The antiderivative of 1 over u squared, I would, if I were you, write this as u to the negative 2 du. So I'm going to add 1. So that'll be u to the negative 1 over negative 1. So I would write that as negative 1 over u. Okay, now again, we're looking for the general solution to the differential equation. So if u is equal to y over x, then negative 1 over u is equal to negative x over y. Okay, so I'm going to write negative 1 over u as negative x over y and rewrite the right side. Okay, so you can go through whatever process you want. You can clear fraction, you can do all that good stuff. But I know that the solution, general solution to the differential equation will end up being negative x over ln of x plus c. There you have it. There's your general solution to that differential equation. All right, let's continue with another example. All right. Different formatting here. dy dx is not isolated yet, as well as we are now looking for the particular solution to this differential equation. So let's start first by isolating dy dx. So dy dx will equal y squared minus x squared over xy. Okay, I'm going to write my buddies over here. Here you are. There's u. There's y. Hey there, dy dx. How are you? After getting interrupted by a student, so inconvenient. Let's continue this problem. Okay, so we're going to do some substitutions, and no different than what we've been doing up to this point. Dy dx is equal to du dx times x plus u. And anywhere you see a y squared, I'm going to plug in a ux squared, right? So y squared equals u squared x squared. So this would give me u squared x squared minus x squared over x times y. Now x times y is going to be x times ux, which would be ux squared. So I'd have a u x squared. Okay, now what I can do here is I can do some work on that right side. I'm going to rewrite the left side, and I want you to see this come to fruition in this way. I'm going to factor out an x squared on the top, which would give me u squared minus 1. And on the bottom, I'm just going to kind of reorganize things. And you'll see that the x squareds, they reduce. All right, so I get this expression, du dx times x plus u is equal to u squared minus 1 over u. All right, so I'm going to subtract u from both sides. If I do that, I get du dx times x is equal to, I'm going to get u squared minus 1 over u minus, and I'm going to write u, right, minus u, but actually I'm going to rewrite u as u squared over u so I can get a common denominator. All right, so let's continue this. Du dx, simplifying, times x is equal to, well, u squared minus u squared is just 0. So I'll get a negative 1 over u. Okay, let's make sure that we've got all our algebra appropriately defined here. Yep, I think we're good. Okay, so now we're separable. Okay, so let's separate the variables. Let me separate here in terms of u and x. So I would have a negative u du is equal to 1 over x dx. All right, time for some integration. All right, so what would that be? That would be negative u squared over 2 is equal to the natural log of x plus c. All right, let's see what happens next. I'm just going to clean this up a little bit and write that u squared is equal to negative 2. Actually, hold on. Let's back that up. I forgot we were going to go with a particular solution here. So let's actually isolate this and call this in terms of y and x instead of in terms of u. So I'm going to call this negative y over x squared over 2 is equal to ln of x plus c. All right, so when x is 1, y is said to be 0. This is actually pretty nice. If I plug a 0 in for y and a 1 in for x, on the left side I get a 0. On the right side I get the natural log of 1 plus c. And the natural log of 1, of course, is 0. So I get 0 equals 0 plus c, therefore c equals 0. Okay, so now I'm going to go back to this and write that I've got negative y over x, quantity squared, over 2 is equal to the natural log of x, and plus c would just be plus 0. So y squared over x squared is equal to negative 2 ln of x. All right, now I'm running out of space here. Let's see if I can move some things around here. And again, I'm going to employ this idea that I'm going to keep y squared alone on one side. Therefore, multiplying by x squared on both sides would give me the following. And there you go. There's our particular solution to that differential equation. We got one more example using this homogeneous method in order to separate variables. Let's get to it. All right, example 5. Now in example 5, we're going to do a slightly different substitution. Right? IB is prompting us with the fact that we're going to use this substitution that u equals x plus y. Okay, so if u equals x plus y, then y equals u minus x. So I'm going to do a quick substitution here. Okay, showing that dy dx is equal to x plus u minus x. Okay, interesting. So that tells me that dy dx is then equal to u. Okay, now when I find dy dx in terms of u and x, okay, if I were to differentiate, it looks like dy dx is equal to du dx minus 1. Okay, so I'm going to do that substitution here. Du dx minus 1 is equal to u. Thus, du dx is equal to u plus 1. Okay, interesting. Let's look at part 2. Hence, show that the general solution is given by the following. Okay, so now if you look at du dx being equal to u plus 1, this is separable. Okay, I'm going to divide both sides by u plus 1 and multiply both sides by dx. Now I've got a separable differential equation, or it has been separated, and I want to show that the general solution is given by x plus y plus 1 equals k e to the x. Okay, so integral of 1 over u plus 1 is the natural log of u plus 1. Integral of dx is x plus c. Okay, I wonder if we're given a initial condition. We are not. Okay, that's where the k is going to come into play. All right, so I'm going to take e to the power of both sides. All right, and what that does on that left side is that leaves me with u plus 1. And e to the x plus c is the same as e to the x times e to the c. Now, I'm going to consider e to the c some constant k. So I should have u plus 1 is equal to k times e to the x. I like that. Now, what was u? Well, I think u from above was x plus y, right? U equals x plus y. Therefore, x plus y plus 1 is equal to k e to the x. And there you have it, guys. There's the general solution to that differential equation. Now, a substitution like u equals x plus y is not going to be one that you're going to be held accountable for kind of drumming up. It will be given to you, right? We're traditionally going to work with the homogeneous substitution method of u equals y over x or y equals ux. Okay, so be comfortable with this and adjust appropriately when prompted with something else. All right, that's it. Day number 3, homogeneous method for finding particular and general solutions to differential equations. Have a great day. We'll see you in the next video.